these structures. Moduli spaces. And yeah, it's kind of embarrassingly elementary thing that I'm going to tell you, but on the other hand, the number of authors is quite impressive. So, so this is a joint work with Anton, with Florian, and with Jan. And yeah, so let me start with some basically overview of the talk. What's going to happen, and then there will be maybe more things. So if you take a surface which is compact, oriented, possibly with boundaries, so something like might have a boundary, maybe more components. So then, if you consider the loops on this surface, then more precisely, homotopy classes of loops on sigma, I'll explain more properly in a moment. Then on this guy, we have a Lie bracket. Like table. There is a Lie bracket which is called the Goldman bracket. And it corresponds to something on the other side. So the other side is like moduli space of flat connections or character varieties. So something which corresponds to is the Poisson structure. Poisson bracket. Now, okay, this is probably not very standard notation. It's the moduli space of sigma, and we pick up some group, and to have a Poisson bracket, then we need to have some invariant pairing on the Lie algebra of G, and the correspondence between those two things is for when G is equal to GLN. So that bracket was okay. This was the first thing, knowing the Poisson structure, and then Goldman discovered how it gives rise to this nice Lie bracket on loops. But there is something similar happening here, which is there is also Lie co-bracket, which is called 2IF by this discoverer. 2IF co-bracket. And it's not quite obvious what was the corresponding structure on moduli spaces, and this is what to much extent this is what this talk is about. Like filling this space. So what's happening here is we will have more than just the Poisson structure on moduli spaces. So there will be some kind of enhanced Poisson structure. And the thing is, actually, I'll explain in a moment, it works, but this Poisson structure cannot be ordinary Poisson structure. It has to be odd Poisson structure. So it will work only when the pairing on our Lie algebra is actually odd. Okay. And this enhanced thing is what is called a BD structure. And the correspondence is when for G we take some sort of analog of GLN, which exists in the world of supergroups. So that's what is called UN. And then there is a lot of fun around this stuff. So that's what this talk is supposed to be about. Okay, so let me start with this very standard Goldman bracket, and also with the corresponding co-bracket. So first part is Goldman bracket by algebra. Okay, so let us take loops on sigma. So there is this wonderful notation that I do not master. It's a script G sigma. So for that we take homotopy classes of 3 loops on sigma. Homotopy classes of loops on sigma, and then take those, let's say, the 3 abelian group generated by this guy. So I'm not sure how to note it, Z generated by this thing, or if you prefer, it's a shorter notation, definitely it should be the H0 of the free loop space of sigma. And yeah, so this guy is now a Lie algebra. So the Lie bracket is the Goldman bracket, and it's given by the formula. So we could have 2 loops, gamma 1, gamma 2. Then the outcome is going to be a linear combination of loops, and it's given by the following way. So we actually, I should say, gamma and gamma 2 are classes of loops, so let us pick some particular representatives of those in those classes, and let's suppose that they intersect transversely, so there are finitely many points of intersections, and everything looks nice. So we take the sum of all intersections. Gamma 1 and gamma 2. And then what one needs to do whenever we see such an intersection point, our loops are oriented. I will draw it also with orientation. So here is our intersection point. So we just modify our pair of loops and only around this point to obtain a single loop. So we replace it with this kind of thing, except that there is some little trouble with the sign. So this is how it works if this is gamma 1 and the other one is gamma 2, and I'm using so now we need to use the orientation of the surface, so if you're using the standard orientation, or if it's the opposite orientation, then we need to take the opposite sign. So if it's like this, 1, 2, then we replace it with minus. Okay, and now if you take this moduli space of flat connections on sigma with the group GLM, then we have a map going from this Lie algebra, which is sigma, to functions something from here, and which is given simply by sending a loop to the trace of these orthogonals along gamma. And the statement is, or that's about basically how Goldman discovered the Lie bracket here, that the statement is that this is a homomorphism of free algebras. So the Lie bracket goes here, goes to the Poisson bracket there. Homomorphism, or if you prefer to work with Poisson algebras, then enhance this guy to become a Poisson algebra. It's a good idea. So for that, we would just say symmetric algebra generated by sigma two functions on the moduli space. So this is a Poisson. Yeah, there's some better statement saying that, roughly speaking, when you take the limit and go into infinity, and probably to replace Z by whatever is our base yield, then this becomes this becomes an isomorphism.
Sorry to intervene, but transmitting between okay, it works.
Yeah, sorry, I'll try to. I forgot about this setup.
Yeah.
Yes.
That's why I'm saying it.
Yeah. Okay, I'll try to stay always on one side. But anyway, it's some kind of stuff. Hopefully, very standard stuff. Now, how about this two-right co-bracket? So this guy will, let's call it delta, going from G sigma to square 2 G sigma. And let us try to do the same formula. I cannot go there, but the same kind of formula, but now apply it to a single loop. So delta of sum gamma is by definition the sum over all self-intersections. Of gamma. And so what do we do when we see self-intersection? Then we replace it as before by this kind of resolution. So now it's actually split gamma into two loops. So it's like, I'll use like this is one, this one is the second one. And the way how we should see it is that when we take the wedge product, we first take this one and then we take the second one. Unless it's the other way around, but it doesn't matter. It would only like change the sign. So there is this wedge here. Yes. Now I'm cheating actually, so people here would recognize. So maybe let me still cheat even more and switch the board. So to see that this bracket is well defined, okay, one now need to show that it's actually independent of the choice of representatives. That if you try moving gamma 1 and gamma 2 around, of course those intersections will change, but that you will be getting in the end same result. It can be done. Camera. If you're following me, it's okay. And if you try to do the same thing here, then it will fail. So this is not a well-defined thing. It will fail, for example, if you do just something like this, which is, of course, that's equal to the thing. So if you have a portion of loop which looks like that. But still, if you apply delta here, then there is no, at least in this part of the surface, there is no self-intersection, so you could just get 0, but there will be a contribution coming from this self-intersection. So the only way out is that we need to impose a new relation. That if you have a contractible loop, like that, then this is equal to 0. So, okay, so that was the high point of my talk. So let's just impose this relation. I'll put here, let's see, 0. At least that's one way how to deal with it. There is another way how to deal with it by using with some framing on the surface. Let me just keep this stuff. This Goldman bracket is well defined also on this G0, so it is not a big deal if you pass from G to G0. And now the kind of question is, what is the moduli space interpretation? So maybe I should add to this now G sigma 0 with its Goldman bracket. That thing is to write co-bracket. So this guy is the Riba algebra. It is slightly better than just the Riba algebra. It is what is called involutive. Involutive means the following thing: that if we take something, apply the coproduct, the cobracket, and then we apply the Lie bracket, this is equal to 0. And it, in the world of Hopf algebra, it corresponds to the square of the antipode being the identity. So it is like a relatively natural thing to impose. But anyway, it is true. And the question is about moduli space. Interpretation of this thing. So to get to this let's now start part 2. It will be because in the end that will be this moduli space interpretation. So let me start with some definitions. So if you take a commutative superalgebra, that's by definition a Z mod 2Z Z graded. Algebra. And for commutativity or for any time you want to exchange two things, you need to use the sign also. Whenever you're exchanging two odd things, you need to multiply it by -1. So it's kind of graded commutative algebra in the sense. So then a BD operator actually, can the camera see me when I'm writing down?
Yes.
Yeah, please. And can you see me? Or maybe it doesn't matter. So a BD operator is what? So it's supposed to be just a linear map going from A to A with squares to 0, so it's like a differential. And then there are two conditions which might look slightly random. First one is probably okay, that delta of 1 is 0, and the last one is that delta is a second-order differential operator. So what does this being second-order differential operator actually mean? So, as I said, this is supposed to be a super elementary talk, so I will actually explain it in a second. So being second-order differential operator means that if you take any f and g in A, and first, if you commute delta with this zero order operator, which is just multiplication by f. So this is supposed to be a first order operator, which then means, again by definition, that if you commute it with this zero order operator, multiplying by g, then this is now a zeroth order operator. So it's just multiplication by some particular element of A. And we can compute that element relatively easily by sending it on 1. So we'll let it act on 1. And then using this guy, that will help us to some extent, so then we'll get that this thing is delta of f times g, and then plus minus, there are those sign rules, f delta g, and some other plus minus g delta f. So that is a functional element of A, and let us denote it by Poisson bracket of f with g, and indeed this guy is a Poisson bracket on our algebra. It's a Poisson bracket. So the parity of this function is the parity of f plus the parity of g plus 1. So it satisfies the properties of Poisson bracket modulo sum sign. So in this sense, a PV operator is kind of enhancement of a Poisson structure.
What's the bracket of the left-hand side in the Poisson sign? What's the left-hand side of the bracket of delta and f?
Left-hand side of the bracket of delta and
Yeah.
this thing. Okay. By this f dot, I mean just the map from A to A where we multiply everybody with f.
Is it commutator?
Yes, the commutator. Yes, sorry. It is the graded commutator. Okay, so now this commutative algebra with a PV operator is called a PV algebra, as you can imagine. And let me give you an example. So if we take a involutive Levi algebra, as was happening there, so if H is an involutive. So should I? Okay, sorry. By algebra with some. Okay, so we have some bracket and co-bracket. Then the just one algebra of H is a easy algebra. And how does it work? So if you have somebody from some element from here, V1 tensor of just wedge. Okay, and we want to apply delta on that, then sort of maybe slightly schematically, the delta is the sum of the bracket and the co-bracket. But the way it's done is that this part, it goes through all possible pairs. So we would take there would be maybe some some VI inside, and you take them, this and that, compute the bracket, and then place it with some sign somewhere. That doesn't really matter. And there is this delta part, which simply, again, takes somebody and replaces it with the corresponding co-bracket at that place, maybe again with some sign. Okay, so that's a basic example of a BB algebra. And so in particular, that gives us that wedge of the G0 sigma is a BB algebra. Now, okay, here I explain it sort of too schematically what it was. So let me now explain how this guy is exactly a BV algebra now in a picture. So what actually is an element from here? So this would be a collection of loops, though we need to remember to some extent the order of those loops up to some sign. It's a Grassmann algebra. But no. So an element from here would be something. But if you just look at such a picture from, if it's more complicated, then you actually don't know how many loops there are. We just something like that. And so, how does this BV operator act here? You simply take the sum over all intersections, whether they are self-intersections or non-self intersections. So anyway, you cannot distinguish them just by looking at the picture. So each time we see an intersection, so we take the sum over all such things. So each time we see an intersection, then okay, we need to know what the orientation is. So let's suppose that it goes like this and like that. Then we resolve it as before. Just sum over all these possibilities. And then there are some difficult signs. But signs are always difficult, so let me just see. So actually, that this thing as a BV algebra is a very, very natural thing. Okay. So now, yes.
Two remarks. One technical remark.
I should. Yes, the camera is a little bit.
We also have some small problem with sound. They only hear what you are saying. They don't hear what we are saying.
So I should repeat whenever somebody asks a question.
When we ask the question, repeat. And I now to ask the question.
Okay, and I'll repeat.
So how is it? So it's a theorem, right? That this arrangement, match G, or I mean, kind of maybe you can indicate. I mean, is it obvious? Is it like computational? Write this statement that you.
Okay, so yes, so roughly speaking, Anton's question is whether one can see now. I said here all kind of nonsense, but whether one can see now directly that this Grassmann algebra generated by those loops with this operator, that it actually is a BV algebra. So yes, it is possible to see it like kind of straight away. The one needs to use those difficult signs maybe to some extent. So the thing is that if you were computing delta squared, so it would mean that we resolve one point and then we resolve another point. And the thing is, such a thing would appear there twice because we can either resolve first this one and then this one, or we can resolve first this one and then that one. And actually, they will occur with the opposite signs. So that's why they cancel each other.
But I thought homotopy independence, or isn't it really that's more?
Okay, so
you repeat what I'm saying. Right?
Okay, so It's like in school. So the second question is why it is actually why the delta is actually well defined, why it's independent of the choice of representatives. Yeah, or the only thing I can say that yes, one can see it, but I will not explain how. I mean that you just start using all those Reidemeister whatever moves, and how those loops can pass through, portions of loops can pass through each other, and then you need to. That's one way at least. That then you need to show that the outcome is independent of how you do it, and it's not difficult, as you can imagine, and there is some work to be done. But in the end, like I already said, just for the co-bracket, that it can be verified, but I didn't explain how it is verified. So it's basically the same stuff. It's not, the proof is not any different. Okay, now there is sort of very short part 3, which is only an advertisement to some extent. So it's Poisson and PG structures on moduli spaces. And so let me just remind some stuff that if you have a Lie group, and then on the Lie algebra we have a invariant pairing, then from that we can say that the algebra of functions on the modular space is Poisson. And kind of nothing now changes if instead of a group we take a supergroup, but something changes if we change the parity of the pairing, but only very mildly. So if now G is a supergroup, and if I keep simply even pairing, such an ordinary pairing as before, then it is still going to be a Poisson superalgebra. But if now for that pairing take something which is ordered, but still invariant and non-degenerate and everything as it should be, then what we will get that this is going to be an odd Poisson algebra. We will have there an odd Poisson, but it will become ordered. But in fact, something stronger is true. So that's the point of this thing. So there is a theorem by all those 4 people, or if there are more people who want to join them. So, I put in 2 parts. So the first part will be precise. So if I'm talking about this setup, it corresponds to this setup. So if we suppose that G is also unimodular, then this algebra is actually in a natural way an easy algebra. Oh, G is naturally. So there's like this little difference that you can already see that if you have a ordinary algebra with an invariant pairing, then that's automatically unimodular. But this is not true for odd pairings, and that's something like what all of this is about in some sense. So all those big structures are about talking to some extent about volumes in a world where volumes have difficulties to either exist or at least are not always naturally defined. And so the second part is what happens when it is not unimodular. So in general, not unimodular. So then we need to choose some extra structure on sigma. So we need to choose a framing. I'll explain more precisely what it means. Let's just imagine that we have a non-zero vector field. Let's say non-vanishing vector field. So then the same is true. Okay. And now the last thing before the break. So it's part third question here. So the last thing before the break is I call it queer things. So this will be we're talking just about some particular Lie supergroup with a knot pairing. So let us start with a vector space W, finite dimensional. Vector space, and then we define a superalgebra, associative superalgebra. So this is an ordinary vector space, it's not graded or anything. There's superalgebra little q of W, just simply endomorphisms of W, just matrices, and tensor with a Clifford algebra with one generator. So tensor with algebra with a generator epsilon, such that epsilon squared is equal to say 1. But this epsilon is supposed to be ordered, so that's how it becomes a graded algebra, superalgebra. Order. And so if you want, this thing is 3.1. And also on this algebra, we have there is a natural odd trace. On QW, which, okay, write it explicitly, odd trace of some A plus B times epsilon is simply the trace of B. So it keeps only the matrix which multiplies the epsilon and then takes the trace. And it does satisfy the cyclic property of a trace, so it's okay. Okay. On trace of xy. But it is odd because it changes the parity. It's non-zero only on odd elements, but the outcome is a number. It's an even thing. Okay, so then naturally this Q of W is also a Lie algebra or Lie superalgebra. Simply by the commutator. Right? So it's an algebra, therefore it's by the usual nonsense. It's also a Lie algebra. It's actually unimodular. the corresponding group is very easy to find. Those are just invertible elements. The group QW, and we can see there's a part of this little cube of W such that say determinant of A is 0. So it's a supergroup. Now this odd tracing is an invariant function here, and so we have the second theorem. That there is actually a BV map, a map of BV algebras, which goes from our BV algebra, so this wedge of G sigma 0 to functions on this modular space sigma with Q for whatever W. Yes?
Sorry, you just said invertible elements, but an element be epsilon can't be just invertible.
Oh, okay. What I should have said is the even part which matters. So the even part should be invertible. I maybe don't want to talk too much about supermanifold because it always confuses everybody. But yes, this. We should look at what's happening in the body. So these are the two things are only those that are not multiplied by epsilon in some sense, and those should be invertible.
But in particular, A plus B epsilon may not necessarily be invertible.
Maybe, yeah, I don't know. But those inhomogeneous things are anyway kind of thick. So one should always look at either. Yeah, okay. Anyway, so that's the condition. That's how it becomes it. That's how it becomes it. Yes. So here we are. So what is this map? It's precisely the same thing that we saw for. Sorry, I did not repeat your question. Oh, but now I forgot your question. Yes, so I'm now kind of at the end of almost. So it's the same kind of map as we saw for the Goldman, just for the Goldman bracket, or when there was S of G sigma without any zero, and here there was GLN or GLW, doesn't matter. So I just have to tell you what to do with a single loop, and a single loop is now sent to the odd trace of the holonomy. Along gamma. Okay, so that's the analog of what was happening for GLM. Now it sort of explains some kind of modular space origin of this of the derived co-bracket or of the BV structure on this algebra, and I think it's a good place for this stuff.
So maybe you can ask for questions both from both parts of the audience.
Okay, so are there any questions from anybody anywhere in the world?
Can I ask a question? Can you hear me?
Okay, so
I'll tell you. Yeah.
Okay.
So yeah, what we can.
So what's why does this already in the first case? Why does one need to restrict to GLN?
Why GLN is already proposed?
Okay, I'll kind of get to it in some, or hopefully. But roughly speaking, what is happening in general? There's a formula what to do when you have an intersection. There is some sort of a chord that one needs to plug in. And in the case of GLN, and when you're using the trace, so it's somehow important, those functions are given by traces in the defining representation, and then this guy is actually, the question is whether this guy is equal to that thing. And it's a sort of slightly special property. So that's why, okay, at least it works for GLN and for the trace, and it doesn't work for other functions. But okay, there might be some other functions for which it works. But anyway, that's roughly.